thank the organizers for inviting me to speak here. I want to tell you about some work that I've done with my two French collaborators, Antoine Benay and Pierre Deplace, both at ENS Lyon. And the work I'll describe is in this recent article, although at the end I'll tell you some future directions that we're working on. So the outline of this talk is first, well, Kelvin's name was already mentioned in the introduction, and he was certainly interested in topological entities, vortex rings, and so on. But we'll see that actually he is likely the first discoverer of the topological edge mode, and that has its physical realization in the planetary atmospheric and oceanic dynamics, which I'll discuss. And then I want to talk about broken discrete symmetries, especially time reversal symmetry. And we'll do some simple numerical simulations and look at some observations. Look at some other mechanical topological waves that have a similar origin. And then I'll be progressively turning to a more mathematical point of view, look at the shallow water equations, which are the simplest equations that support these kinds of waves, and compute the Chern number for these shallow water equations, demonstrate that these waves are protected from scattering, and this opens up some interesting questions about nonlinear effects. Hydrodynamics ultimately is nonlinear, and I'll talk about some other systems under investigation. So the El Nino is a phenomenon in which there is a body of warm water in the equatorial Pacific that moves from one side of the Pacific, the western side, over to the eastern side off of South America. And here, this color scale indicates an anomaly in the height of the Pacific Ocean as measured by a satellite. The idea is that warmer water expands and therefore pushes the water upwards. So the scale here is about plus or minus 20 centimeters or so. So this is a movie, and this shows the progression of a wave across the equatorial Pacific from El Nino that occurred in 2009, 2010. It was of moderate strength, and you can see this pulse going across, actually two pulses, delivering warm water off of South America, which had a number of climatological effects, which I might discuss briefly at the end.
The scale is months there, or?
Yes, so this would be over from December through February. So typically the El Ninos occur during the winter months, and you can see the time bar there going. Here's a vertical cross-section showing, this is actually a more recent and stronger El Nino from 2015, and you will be able to see this pulse of warm water going across, and also there's some vertical structure here. And we see what's called the thermocline rising up as this body of warm water moves across the ocean. So I want to argue this is actually a topological edge mode. So just to briefly mention some of the larger effects of this El Nino is that during the El Nino phase, we have this pool of warm water over here, which tends to promote convection, because it heats the air, there's moisture, it goes up, and so that changes the atmospheric circulation, even though this was initially a phenomenon in the ocean, changes something called the Walker circulation, and that leads to a reversal of the flow of this atmospheric circulation, and it's that reversal that leads to a restoration back to the other phase, which is called La Nina, and we get a kind of pulsing. It's a nonlinear oscillator that has some interesting dynamics. It's chaotic. It appears to be chaotic. It's something that's been a challenge for climate models to accurately reproduce. So
what's the temperature? It was a few. Was it? I saw something like 5 degrees centigrade. In the water.
No, a few degrees centigrade would be the range, yeah, from that. So I've been studying geophysical fluid dynamics for a number of years. And if I'd been paying attention more closely, I would have realized that this topological wave was screaming at us, and we should have noticed it. So in this classic textbook, for instance, there's this figure, which I, for some reason, just ignored, mainly because I was focusing on the regions of the Earth and atmosphere and oceans away from the equator. The equatorial region is rather complicated because the Coriolis force is weak there, and usually, in fact, most of the intellectual progress in the field of geophysical fluid dynamics came from using the fact that the Coriolis force is a dominant force, and that tends to have a linearizing effect on the motion of the atmosphere. And so if we have linear equations, of course, we can make more progress. But I didn't stay away from the equatorial region, but here is the dispersion of waves in the equatorial region. A couple year or two ago, we had a search for a condensed matter experimentalist at Brown, and as the candidates would come through my office, I would dig up this book and show it to them. They were wondering why I was showing them this book, but then I showed them this figure, and without saying any words, of course, they immediately recognized that this was suggesting some topological wave. So this is the Kelvin wave. And if we go back into the literature into 1879, yes?
Can I ask, how is the spectrum kept?
Yeah, we'll talk about that.
Okay.
I'll go back to that. We have Kelvin's paper on gravitational oscillations of rotating water, William Thomson. And here is the crucial equation. Here we see some exponentially decreasing wave going away from a boundary. He's looking at waves along the edge of a continent, thinking about, in particular, waves in the English Channel, oscillating, and the frequency here is linearly proportional to the wave number. So this is a linearly dispersing wave that is trapped along the boundary of a system. And so I think this is probably our first example of a topological wave. You can go back and read this paper. It's quite readable. And so I'll show you, I'll basically guide you through the analysis of this, although we're going to be looking at the equatorial region. So let's talk about the symmetries of the system. So in classical mechanics, just as in quantum field theory, we have the CPT theorem. And in this context, we can think about a rotating planet rotating around some axis here at an angular rate of rotation omega. And if we reflect this planet in a mirror, then the rotation direction reverses. So that's our parity operation. And then, of course, if we time reverse, then we'll restore the rotation. And in this sense, there's no charge in this case because I'm going to be considering neutral fluids. Mathematically, the Coriolis force, as I'm sure all of you know, is expressed in this type of formula where the acceleration in a rotating frame is related to F, the forces divided by the mass, but has these additional terms due to the fact that we're in a non-inertial frame. And this is the most important one in geophysical fluid dynamics, 2 times the angular rate of rotation crossed into the velocity of our partials moving on the surface of the sphere. This is the centrifugal force, which is usually small in geophysical systems. And so what matters the most is since most of the motion is in the horizontal, then it's the vertical component of the Coriolis, of this angular rotation that matters. So if we're at a given latitude on our planet, we look at the dot product of omega dotted into the unit radial vector. That gives us 2 omega times the cosine of the colatitude. And so this is the usual Foucault pendulum term, and I believe that's why the symbol F is reserved for that. So now let's look at equatorial waves. And I'm going to look at these from so this is another textbook result. We're going to be deriving this in a moment. But the spectrum is a little bit more complicated than that first spectrum that I showed you, which suppressed a number of the other waves in the system. So if we have shallow water, which I'll define in a moment, and look at rotating on a rotating sphere, and look at the waves near the equator where the sense of time reversal symmetry changes. When we go from the northern hemisphere to the southern hemisphere, the sign of the Coriolis force reverses. So right at the boundary, something interesting is happening because we have these two states in opposite, breaking time reversal symmetry in an opposite way. So there's a boundary between them. And we have this collection of waves, gravity waves, planetary waves, the Kelvin wave that we saw before that's linearly dispersing, and something called the Unai wave. And so I'm going to illustrate those now, at least some of them in the simulation. When our paper was reviewed, we had some nice comments from some of the referees, and one of them said, question of why the equator supports a unidirectional wave, a Kelvin wave, is interesting scientifically and important mathematically. I've asked the question myself and been unsatisfied with my own answer, as well as the answer of other atmosphere ocean scientists. So it was known since the time of Kelvin that these were solutions to the wave equation for a rotating system, but there was a feeling that there was something deeper going on, and it wasn't understood what that deeper thing was. So especially this dispersion of waves near the equatorial region was rather mysterious. Okay, so now we're going to look at some simple simulations just to get a feeling for what's going on. So we're going to look at something called the two-layer model. So in this model, we imagine having a denser fluid below a less dense fluid, and therefore there's a restoring force. If we push up, say, the denser fluid, it will want to go down because of gravity. And so we might imagine this is a colder fluid and this is a warmer fluid. And we'll look at excitations of this interface between the two fluids as a function of latitude and longitude. So here I've done an experiment on the sphere, a numerical experiment on the sphere, where I've dropped a rock onto this fluid, and we see a nice spherical wave or circular wave go out. Yes?
These are inviscid equations on a zero topography, smooth boundary.
On a sphere.
On the sphere. Yeah.
On a sphere, but not rotating at the moment. Okay. So so the wave goes out, it comes to the antipode of the sphere, and then just passes through and comes back to the origin. So on a cylindrical coordinate system, this is what the same wave looks like. It just goes and comes back, and then it'll just bounce back and forth. So now I'm going to turn on the rotation of the sphere. Everything else is the same. Same initial condition, everything is the same. And there's our Kelvin wave. You can see that it's non-dispersing, and it's trapped in the equatorial region. It's trapped in the equatorial region because any parcel of fluid that tries to move away from the equator is deflected by the Coriolis force back towards the equator. This is the reason why there's that gap in the spectrum, why there are those modes at non-zero frequency. That frequency gap is, in fact, equal to 2 omega, the rotation frequency. But there's actually two waves. This one is symmetric with respect to the equator, reflecting north and south. There's also an anti-symmetric wave. This one, which you can see is dispersing. Its phase and group velocities are different. And that's the Unai wave. That's the second wave that we saw in the spectrum. There's a fourth class of waves. So I've talked about the Kelvin and Unai waves. There's also, I said there are these gravity waves that are gapped by the rotation of the Earth. That's just simply what's trapping the modes here in the equatorial region. Then there are these Rossby waves. These are long wavelength waves that we'll see emerge from the mathematics. Those are the waves that basically govern the weather at high latitudes. So if you want to run some of these simulations yourself, you're welcome to. I put an app on the Mac App Store for free called GCM, and you can download it and you can play with it. These run easily on the laptop. So what is the observational evidence for these waves? This is observations of the power spectrum of waves in the equatorial region of the ocean, looking at actually cloud cover, which, as we saw, responds to the position of the warm pool of water in the equatorial Pacific. And so this is wave number versus frequency, and we can see this linearly dispersing mode, the Kelvin wave. And then if we look at the antisymmetric component of those that cloud distribution field, we pick up the Nino wave, which is dispersing, and hence the phase and group velocities are different.
So this is like a Fourier transform of the cloud pattern in space and time?
That's right, yeah.
So now we're looking at the air rather than the water, so
Right.
time scales are very different and
Well,
whether it's
the air is slave to the water. So we're filtering out very short time scales, the atmospheric time scales, and just looking at the time scales that are responding
I
to
see.
the
Okay.
ocean. So as you all know, there are many by now many classical systems that support topological waves. They're usually on lattices, unlike the continuum systems that I've been discussing. But other than that, they share a number of properties with Kelvin waves. And one that I particularly like is this collection of gyroscopes that are all processing in the same directions, and which a wave is, and they're connected by springs. So some energy that's input into the system then propagates, and that's indicated by these colors. And so we see this edge mode propagating around this collection. And it goes in one preferred direction because the system breaks time reversal symmetry due to the fact that each of these gyros is processing. Okay, so now let's get to some of the mathematics of this system. So the simplest set of equations that support these modes of the shallow water equations, these are the ones that Kelvin looked at in 1879. And we're going to linearize them. So what are these equations? Well, we think of again, a cross-section of our fluid. So we have a denser fluid underneath a lighter fluid, and these are the two spatial directions, and we have some height field h. And our partial differential equations that govern this are these equations. So this first equation is basically reflecting the conservation of mass. It's just saying that if this height changes, then the fluid is being pushed out or pushed in. And so we have a current, which is basically the height of the field times the velocity of its field. So that's the amount of the quantity of that fluid, that infinitesimal fluid that's moving in and out. So this is a conservation of mass. And then we have the momentum equation that says that the time derivative of the velocity field, u, being the two components in the horizontal, and here we have the effective derivative because we're thinking about a parcel of fluid moving. So this is a nonlinearity, which we're going to shortly dispense with. And this responds to various forces. The two forces are the force of gravity. So this is the restoring force of buoyancy that wants to push this bubble of dense fluid down, and then the Coriolis force here. So those are the two competing forces that are going to act together to give us these topological waves. So we can non-dimensionalize this system. There's a characteristic speed in the system of gravity waves, the force of acceleration times the average height of the fluid, and then there's a length scale, which we can form by dividing by the rotation frequency. And so we're going to look at small deviations about some average height for those fluids. So let's non-dimensionalize the height field and look at those deviations with respect to capital H, and we'll also remove the dimensionality of the velocity and time and so on. So the end result is this system of three partial differential equations, where linear partial differential equations, because I've assumed that the velocities are small, and we can express this, much like in the previous talk, in a Schrödinger equation-like form by introducing this three-component wave function, which involves the the height of the fluid, and then the x and y components of velocity. So it's this three-band structure that's going to give us a non-trivial band structure that gives us gaps and allows for the possibility of a topological wave even without any lattice. So now we'll use the bulk edge correspondence, and what that tells us in this case is that instead of analyzing the complicated equatorial region where the Coriolis force changes sign, we can go far away from that equatorial region and just fix the Coriolis force to be a constant. And we'll look at this little region away and then analyze the wave functions in that for constant f. If we are working with constant f, that means that we can work with plane waves because we have translational symmetry in x and y direction. Our three PDEs just become a 3x3 matrix, and we can diagonalize it easily enough. It has a particle-hole symmetry reflecting the fact that these wave functions are real, and this is what the spectrum looks like. We have these two gap modes, which are called the Poincare gravity waves, plus a zero mode. That zero mode is the classic thing you learn about when you're first learning about weather, and you think about a high pressure zone. The air can circulate around that high pressure zone, balancing the Coriolis force. That Coriolis force provides the acceleration to keep the air in a constant circular motion. That's the zero frequency mode, which when we then account for the fact that the Coriolis force varies with latitude, becomes a wave, a dispersing wave. Those will be the Rossby waves that were the fourth wave that I was showing you. And the crucial point in looking at these waves is that they have a singularity. They have a singularity as we go through the equator. So we're fixing f, but we allow f to vary as a parameter. We fix it in space, but we imagine decreasing it. And if we look at these components here, we can see that as f goes to 0, the phase dramatically changes. That becomes especially clear if we go to a spherical coordinate system in wave vector space and f space. Then we see that we have a singularity at f equals 0. And it's that singularity that is, of course, the thing that's counted by the Chern number. So we can push it around. Any wave function we can multiply by a phase. But if we get rid of the singularity in one wave function, we get it somewhere else. If we get it rid of it at one pole, we get it at the other pole. It's a little bit like the Dirac monopole, which is at the end of a solenoid. We can, by gauge transformation, move that solenoid around, but there's always some singularity in the Aharonov-Bohm phase as we go around that Dirac wave function. So the net result of this is that the Chern number is 2. It's 2 because there's two waves. There's the Yanai wave and the Kelvin wave. If we had looked at the original problem that Kelvin studied away from the equator, but where the restoring force is provided by a continent, then our Chern number would get 1. We only have a Kelvin wave in that case, and that was the problem that he looked at. So now I wanted to do some numerical experiments looking at a wave at low frequency where we don't have any protection because we have these planetary waves, and a wave at intermediate frequency where if we start with a Kelvin wave, because of the symmetry with respect to the equator, it should remain unchanged. So up here I have a region where I've altered the stratification of my fluid. I've changed the temperature profile so it'll scatter waves. And this first wave is a long wavelength, low frequency wave. And what we're going to see is that as I advance this, it's going to scatter off of this region. And it's going to be converted from a Kelvin wave into this double lobe structure, which are the Rossby waves.
And again, what is the system that you're solving over here?
This is the two-layer model that I described earlier, but I've broken translational symmetry now. So here, the imposed temperature difference between the upper and lower layer has been changed so that the waves in this region are moving more slowly.
And the two-layer system on a sphere again?
On the sphere.
Okay.
Yeah. So this is the equator of the sphere here. And this is the system that supports these equatorial topological waves. But now I'm tickling them. torturing them and making them go through these regions. So down below, here's
And the only-
another.
Sorry, can I just ask another? The only role of temperature is buoyancy, so this is a Boston-esque type.
That's right. Yep. Here's another Kelvin wave, but this is now a shorter wavelength one that's in the gapped region. So when it impinges on this region of the scattering region, it should just pass through. And what we'll see is that indeed it goes right on through and keeps on going. And in fact, one can run this multiple times and it will just keep on going through this region. It's not scattering because there's nothing for it to scatter into.
Energy can be transferred between the Yanai wave and the Kelvin wave,
Right.
but they're both moving in the same direction in this frequency. In this frequency range, they're both moving in the same direction.
They're both moving in the same direction, although at different speeds. But what protects the Kelvin wave from the Yanai wave is symmetry. So I've set it up so that it's symmetric with respect to the equator. So, but you're right. If I had a more generic situation, we could have gone some scattering into a Yanai wave. So probably you've seen these simulations here. In this case, going back to the gyros, this is a high frequency wave that's no longer in the gap, and so it spreads out in throughout the bulk. Over here, some of the gyros have been removed, and we see this topological wave go around that defect. So it's similar to the kind of simulation that I just showed you.
So what is the speed of the Kelvin wave?
So it depends on the situation, but in the case of the Equatorial Pacific, it's on the order, it takes a couple of months for it to go across from one side of the Pacific to the other. But there are Kelvin waves in the atmosphere, various types, and then there's these coastal waves, so it depends on the stratification of the fluid, that is the temperature profile of the fluid, how much restoring force one gets. So that gives you an effective, basically effective constant of gravity, so the velocity varies. Okay, so it looks like I'm about out of time. Let me just touch on one brief thing. We have nonlinear waves, and so it might be interesting to see, investigate how these topological waves handle nonlinearities. So nonlinearities, in the case of a surface ocean wave, of course, lead to breaking of the wave. This is maybe as close as one gets to something like the fractional quantum Hall effect in of course, we have a linear theory for that, but if we're thinking about the interaction between the electrons, which is crucial for the fractional quantum Hall effect, this is roughly the analog. And so here I have three systems of waves, and now, previously the waves entered a region over here where they sped up, and so their amplitude decreased. But now I'm going to put them in through a region where they're going to slow down. That's going to enhance their amplitude and enhance the effects of nonlinearity. Now in this case, the initial wave was weak enough so that it emerged unscathed. But if we look at this simulation, this is a wave of moderate amplitude, and as it goes into this region that has slower speed, you can see that the wave is highly distorted as it emerges from that region. So nonlinearity's had a strong effect here. And I think this would be an interesting region, or interesting problem for mathematicians to think about, how to deal with nonlinearity for these topological waves. So there are many other topologically protected fluid wave systems. As I mentioned, there's these edge modes at the edges, boundaries of ocean basins. There's Kelvin waves in the atmosphere that are responsible or partly responsible for other known climate effects, such as the quasi-biennial oscillation and something called the Madden-Julian oscillation. And we'd like to have a way to use these topological ideas to observe these directly, to diagnose them from observation, perhaps directly calculating a Chern number. So that's something we're thinking about. There's some planets show superrotation. That's the phenomena where the atmosphere at the equator has winds blowing in the direction of the rotation of the planet. Earth isn't like that because of the trade winds. They go in the opposite direction, but Titan and Venus are. And it's been suggested that in the ancient past, Earth might have possibly rotated, and that under severe climate change, possibly it could super rotate again, which would be a disaster if it were to happen. And Kelvin waves have been implicated in this phenomenon. Active matter, helium-3, all of these things have characteristics that are similar to the Kelvin waves. And in particular, we have fluids that spontaneously break time reversal symmetry instead of in the presence of some external rotation. And in that case, one can do something called the quasi-linear approximation, which is a kind of mean field theory, to understand the waves in this situation. This leads to non-Hermitian linear theories, and so I'm anxious to learn more about non-Hermitian topological matter. And just to say, here's some recent work by Cristina Marchetti and her collaborators looking at flocking, which spontaneously develops a flow and has an edge mode consequently. And then there's some recent experiments with plasmas that are very similar to our Kelvin waves. Okay, so let me stop here, and I'd be happy to try to answer any questions.
Questions?
So if the modes are chiral when it goes to the shore of South America, let's say, is it going to continue along the shore or something and then bends back at the South and North Pole as well?
That's right. So some of the energy becomes coastal Kelvin waves and propagates along the boundary of South America. Some of it is lost in other ways. So there's dissipation in this system, which I haven't modeled in my simple equations. But for example, if there's warm water at the surface, that will radiate away to space and tend to equalize the temperature difference. That takes place over longer time scales, so often we can ignore that as a first approximation. But if we're trying to get a more complete description of the climate problem, then we have to include those kinds of effects.
In the animation of the Kelvin waves that you showed, what is the length scale in physical units?
In the animation?
Yeah.
Well, I non-dimensionalize also in the numerical simulation. But you can imagine that that was the Earth or some other planetary scale problem. And so, so that was on a sphere.
What about other geometries? Maybe types of tori or cylinders? Or...
Right. So Marchetti looked at on a hyperbolic surface, and so very similar things happened there. I think. Let's see. I have a. So they looked at the sphere, but also this hyperboloid of rotation. And you can see that in both cases that you have these edge modes. So the important point here is that as you go away, in both cases, away from the equator here is basically the region where the normal is perpendicular to the sense of rotation. And so in both cases, the equator is special. It joins these two opposite time reversal breaking places.
Can I ask a question? So two parts, I guess. So first is the shallow water equations are essentially without rotation, transferable, transformed into compressible gas dynamics. So you have an acoustic analog, and of course you don't necessarily have Coriolis terms over there. And so a natural question is, are there compressible systems where you have analogs of this, where you're using something like Coriolis, maybe a mean flow to break symmetry, which people have also observed?
Yes.
So that's question one. And question two is trying to connect two talks that we just heard. You're talking about the discrete limit in the first talk, and the continuum limit. And there are also analogies, because we've been talking a lot about analogies which essentially move across systems. Are there elastic analogies at the continuum limit where you have edge modes which are protected?
Yeah. Let me take up the first question maybe. So I think a very fruitful area to investigate would be plasmas. There's a part so many different waves, actually, for somebody who hasn't really studied plasma physics, that's the first barrier listed. Okay, compared to condensed matter or even geophysics, plasma physics has us down by a number of ways. But there are a number of hints there of topological waves. And so there are these combined acoustic plasma type modes that might be fruitfully studied. So yeah, that's something we're just beginning to think about.
And second question, trying to see whether there are ways in which you can basically exploit this analogy to look at continuum elasticity. If you or other people have thought about it.
I haven't, but I believe others have, and I haven't thought about it too much.
Any other questions? Ashwin?
Beginning of your talk, you mentioned you might comment on some applications for climate and things like that.
Well, yeah. So much of what we know about the climate system comes from observations, and most of the observations have been looking at means or maybe some correlations, but they haven't really focused on these global features that the churn number suggests that we perhaps should sometimes think about. So it's possible that we're missing some of the story, and we're missing some important physics in both atmospheres and oceans by kind of taking such a local point of view. So I'd like to develop tools where we can try to directly detect topological waves from observations that might shed light on these various oscillations that are poorly understood, like the Madden-Julian oscillation. And I think that would be an interesting way to proceed, yeah. Also, climate models are so complicated these days that it's often difficult to sort of discern within the climate model itself what's going on. So these same tools could be applied to the output for climate models. We could hope that we could prove those climate models.
So the topology of a high-genius surface is far more complicated, with more complicated churn numbers. Would that exhibit some interesting fluid dynamics?
I think it certainly could be of intellectual interest. It might be difficult to create such more complicated fluid topologies, so one thing that I didn't show you is we analyzed fluids on a torus that has two equators, and then you would get edge modes for both equators. So
Sorry, you need a monopole in the middle? How do you get the...
So it's just a doubly periodic plane, and since there's periodicity, if I let the Coriolis parameter go from positive to negative, I have to let it go from negative to positive again for periodicity's sake. So there has to be two regions.
Oh, okay. It's a plane with periodic boundary conditions, not a physical torus.
That's right. Yeah. So, but of course, if we wanted to make that experimentally, it might be rather difficult to ask our colleagues to do that. But I'm open to suggestions.
Yeah.
If we look at Jupiter, which has these rings going counter, could those be, or is your mind thinking that there might be a topological reason for the existence of those bands, atmospheric bands, which rotate in opposite directions?
Right. So Jupiter has 10 jets or so. But I don't think topology will explain why they're I don't think it's directly related to this physics, but there might be edge modes along the edges of some of those jets because they break time reversal symmetry in opposite senses. So that might be very interesting.
Last question.
So I'm wondering, so in your model, you actually have a layered model because you have an ocean which has a finite depth.
Yeah.
But let's say you have a sphere of just solids, like our sun or solar, which is just a spherical giant ball of gas.
Yeah.
Does the same argument apply over there as well?
Right. So the real situation is we have what's called a continuously stratified fluid, like the atmosphere is denser down here, lighter up at higher altitude. And so then you could have multiple Kelvin waves. So that's an interesting extension of this work. So we got
It's a Kelvin wave which is kind of propagating along one direction, but actually extended through the entire thickness of the ball.
yeah. So
So you're talking about eternal waves now.
yeah. Well, I guess the ocean is goes some distance to that, but yeah. So if we look at Jupiter, for instance, the atmosphere is very extends to great depth, and there might be all sorts of waves at different depths, and the profile of density may be rather complicated. So yeah, I think these ideas can easily be extended to those kinds of situations.
Thank you.
Okay, thank both speakers for the morning session, and let's continue.